Hi everyone, my name is Shubham and today's my topic is basic system properties. So let's go through it. In this presentation, I'm going to categorize system based on their different properties. That's my topic. First is static and dynamic system. Second is causal and non-causal system. And the third one is time invariant and time variant system. Before we go into the topic, let's understand this. There is a block representing a system. The input to the system is x of t. That's the notation we are going to use. And the output of the system is yt. So as we can see, the arrow is coming from the system and the output. So the output by t depends on input xt and the properties of system. Okay. So let's understand the past, present, and future values. As you can see, there are three examples: y of t equals to x of t minus 1, y of t equals to x of t, and y of t equals to x of t plus 1. We can take any value, t equals to 0, 1, or 2. Let's say t equals to 0. So if we put t equals to 0, so y of 0 equals to x of minus 1, y of 0 equals to x of 0, and in third case, y of 0 equals to x of 1. So as you can see, in first case, y of 0 equals to x of minus 1. So the present value of output y of 0 depends on the past value of input x of minus 1. And in the second case, present value of output y of 0 depends on present value of input x of 0. In third case, the present value of output y of 0 depends on the future value of input x of 0. We can take any value. Suppose we take minus 1. So suppose we take minus 1. So in first case, y of minus 1 equals to x of minus 2. Again, it's the same case. That's the output of y of minus 1 depends on the input of x of minus 2. That's the past value. Okay. So here are some examples: x of minus 2 equals to 1.5, at minus 1 equals to 2.2, at x of o equals to 2.5, and x of 1 equals to 3.0. So there are some examples. At t equals to 0, y of t equals to y at t equals to 0, y of 0 equals to x of minus 1. Okay, in the first case. So it depends on the past value of input. So let's come to our main topic, static system. This system is a memoryless system. It has, as we can see, it has no storage device. So the main point is its output signal depends on present value of input signal. For example, y of t equals to 2 x of t. Suppose we take the value of t equals to 0. So y of 0 equals to 2 of x0. We can see depends the output value of y of 0 only depends on the present value of input. That's why it is a static system. Okay. But what's in the dynamic system? Dynamic system possesses memory. Why the static system is a memoryless system? Because it only stores the present value of input. It doesn't need to store present, past, or future value. So it is a memoryless system. It is no storage device. But the dynamic system has that storage device. So the main point for the dynamic system is a system is said to possess memory if its output depends on past and future value of its input. Let's take the easiest example for this dynamic system: y of t equals to x of t plus x of t minus 1. So according to previous examples, we have seen so many examples like this. So x of t plus x of t minus 1. Okay, so it depends on present and past value of input. This time let's take t equals to 2. So y of 2 equals to x of 2 plus x of 1. So in the first case, in the x of 0, in this case, y of t equals to x of 2. It depends on the present value of input. But in the second term, it says that y of 2 equals to x of 1. So it depends on the past value of input. Okay, so it depends on the present value of input as well as the past value of input. So this is dynamic system because it has to store the past value of input, right? Let's see some more examples of dynamic system. Y of t equals to e of minus t plus 1 of xt, y of t equals to x of 2t. You can see it's clearly it's a dynamic system. Okay. Now let's take a different example. Y of t equals to integral of minus infinity to 2t x of tau d tau. So in this graph we can see what's the integral. Integral is the area step under the curve, right? So we take different points, minus 1, 0, 1, and we can see that area of the curve depends on the past value of input. Okay. At minus 1, if we take minus infinity to t, the area will be this. If we take t equals to 0, area will be this. If we take t equals to 1, area will be this. So obviously it depends the area. The definite integral is area of the curve, right? And the area depends on the past value of t. So of course, if it depends on the past value of t, so it needs a storage device and it's a dynamic system. So our next topic is causal and non-causal system. Let's understand the causal system. Let's go through its definition. Output values of the system is independent of future values of input. As we know what's the future value, we have previously discussed this topic: future value, past value, and present value. The causal system, in the second point, is causal systems are physical, reliable systems. This means that we can see the system in our daily life, causal type of system. Let's move ahead. So the best and easiest examples of causal system are y of t equals to x of t plus x of t minus 1. Suppose that value of t is 1. So the y of 1 equals to x of 1 plus x of 1 minus 1, 0. So we see the first term, y of 1 equals to x of 1. So we can see that it depends on the present value of input in the first term, but in the second term, it depends on the past value of input. So it's a causal system because it depends on the present value of input and past value of inputs, but it doesn't depend on the future value of input. Okay. It can depend on present value or past value of system, or both the value, both present and past value system, but it shouldn't be dependent on the future value. That's the causal system. The second example is y of t equals to x of 3t when t is smaller than 0, and x of t minus 1 when t is greater than equals to 0. So let's solve when t is smaller than equals to 0. Let's solve when t is smaller than equals to 0. Suppose the value of t equals to minus 1. So y of minus 1 equals to x of minus 3. Okay, so y of minus 1 equals to x of minus 3. So the output value of y of minus 1 depends on the past value of input. So it depends on the past value of input. So when t is smaller than 0, output depends on the past value of input. Let's see what happens when t is greater than equals to 0. Let's put t equals to 2. So the y of 2 equals to x of 2 minus 1. Y of 2 equals to x of 1. This is the same. In this case also, present value of output depends on the past value of input. It is a causal system. Let's move ahead to the non-causal system. Output signal depends on future value of input. Future value of input of signal at any instant of time. And the second point is these systems are not physically reliable system, because it's very difficult to find the system that depends on the future value of input. Okay, so it can depend on present value of system or past value of system. The non-causal system is it has to be depend on future value of system. Okay, so the example are, this is the simplest example, y of t equals to x of t plus 1. It depends on the future value of input. Second example is y of t equals to x of t minus 1 plus x of t plus 1. It depends on the past value of system, present value of system, and the future value of system. So it is a non-causal system. Third example is also y of t equals to x of 3 of t. Let's take example t equals to 0, y of 0 equals to x of 3, y of 0 equals to x of 0. It depends on the past present value of system. If we put t equals to 1, y of 1 equals to x of 3, so it is non-causal system because it depends on the future value of input. So let's move ahead. This is the next example. It contains the definite integral. So integral of minus infinity to t plus 1 x of tau d tau. When we see this type of integral, we can directly put limit value to this function. So you can see x of tau becomes x of t plus 1 at t equals to 0. It's x plus 1, so it depends on the future input. If we put minus infinity, it depends on the past input, we can see. So it is non-causal system because it depends on the future input. It doesn't care if it depends on past or present value of input. So the second example is y of t equals to limit minus infinity to t x of 3 tau of d tau. Sorry. If we put t in this, it becomes x of 3t at equals to 1 x of 3, so it depends on the future value of input. Okay, so it is a non-causal system, as we can see. So our next topic is not the main topic, but we can see its definition. Anti-causal system. What was a non-causal system? Let's see. Okay, what was non-causal system? In output signal should depend on future value of input. Okay, it's not that strict that it only has to depend on future value of system, future value of input. It can also depend on present or past value of input. But in the anti-causal system, when the output, let's see, when the output of the system depends only on future value of input, it doesn't have to be depend on present or past value of input, right? So the second example mentioned above is not anti-causal, but it is non-causal. Okay, second example. Second example is y of t equals to x of t minus 1 plus x of t plus x of t plus 1, because it depends on present value system, past value system, and future value system. It depends on present and past, but the anti-causal definition is it only has to be dependent on future value system. So it is not anti-causal, but it is. So our next topic is time invariant and time variant system. So we have to calculate the variance of our system. So let's take an example. Our input signal is xt. We are feeding our input signal to the system, which is represented by this block. We have to calculate its variancy, whether the system is time invariant or time variant. So the system gives the output yt, and we pass this through a system again, which delays the system by t naught. That gives y of t minus t naught. It delays the system by t naught time. Okay. In the second case, instead of delaying the output signal by t, we would give delay to the input signal xt. So we delay the system by t naught, and the output is x of t minus t naught. Then we feed this delayed input to the system, and it gives the y dash t. If this y dash t equals to y of t minus t naught, which was given in the previous case when we delayed the output of yt, if that's the case, then the system is time invariant. But if it is not equals to the y of t minus t naught that was given in the previous case, then it is time variant system. Okay, so let's take a easy example of this of these cases. So it is y of t equals to x of 2t. So in the step 1, we provide in the step 1, here is our output of yt. We delayed this output by t naught, so it is y of t minus t naught. So what is y of t minus t naught? X of 2t. So we multiply t minus t naught by 2, and our final output is x of 2t minus 2t naught. X of 2t minus 2t naught. But in the second step, in the second case, we delayed input itself by t naught. So after delaying the input, it is x of t minus t naught. When we feed this to the system, let's see what the system is doing. The system is doing time scaling, so it is multiplying 2 to the time itself. Okay, it is not 2t minus 2t naught. So the t naught is constant. So this would not be a 2 of t minus t naught. That would be 2t minus t naught because t naught is a constant. So as we can see, the both cases are not equal. So it is time variant system. It's written here in the above example. The system is time variant system, and as both output in step 1 and step 2 are not equal. Let's take the second example, y of t equals to x of cos t. In the first step, we delayed the output by t naught, y of t minus t naught. Y of t equals to x of cos t, so it is x of cos t minus t naught. In the second step, we delayed itself input by t naught and we feed it by the system. So what the system is doing, it's doing changing t to the cos t. Okay, so it would be cos of x of cos t minus t naught. It would not affect that. It would not affect t naught because it's a constant. The system is also time variant system. All these examples are of time variancy. Y of t equals to x of tan t, x into tan t. Okay, y of t cube equals to x t, y of t equals to x t cube. All of these systems are time variant system. So on the basis of these examples, we can conclude the following points to time invariant system. So we have made some conclusions. If the system passes all 3 points, okay, so then the system is time invariant. What's the condition? Let's see. There should be no time scaling. Okay, the coefficients must be constant, and any added subtracted term in the system relationship except input or output signal must be constant or 0. Let's see some example on the basis of our conclusion. So the example is y of t equals to x of t plus 1 plus x of t minus 1. All 3 conclusions satisfied in the above example. So the system is time invariant. So how these conclusions satisfied in the example? There should be no time scaling. It is no time scaling is given here, as you can see. The coefficient must be constant. This is 1 into x t of plus 1 plus 1 into x t of minus 1. So the coefficient is constant. Any added subtracted term in the system relationship must be constant or 0. There is no added or subtracted term in the system relationship. So these satisfy all the 3 conclusions. So it is time invariant system. Okay. So let's take second example. It's based on the integral y of t equals to integral of minus infinity to t x of 3 tau d tau. Okay. So as I have explained before, we can do this as x of 3t. So x of 3t. Let's see if this satisfies all these 3 conditions or not. There is no time scaling. Oh, there is time scaling. So it is not time invariant system. It is time variant system. Okay. Let's talk about the split systems. Split systems are y of t equals to x of t minus 1 when t is smaller than 0 and x of t plus 1 when t greater than equals to 0. Okay, if we remind our three conclusion, this split system satisfy all the 3 conclusion. There is no time scaling. The constant coefficient are constant, 1 into x of t minus 1, 1 into x plus x of t plus 1, and there is no added or subtracted term. So let's see, according to our conclusion, this should be time invariant system, but if we write the system using the below method, but we can write the above system using this method, using this syntax, a of t, x of t minus 1 plus b of t, x of t plus 1. It is the same system, as you can see. If you see it properly, these both are same. A of t equals to 1 when t is smaller than 0, 0 when t is greater than equals to 0, b of t equals to 0 when t is smaller than 0, and 1 when t greater than equals to 0. So when t is smaller than 0, a of t equals to 1 and b of t equals to 0. So this term will be vanished and this term would be left. Y of t equals to x of t minus 1 when t is smaller than 0. And our above example was the same. Y of t equals to x of t minus 1 when t is smaller than 0. Look, it's the same. And when t greater than equals to 0, a of t equals to 0. So the term left is y of t equals to x of t plus 1. So these are the same term. But if we write that problem in this syntax, the 3 conclusions are not satisfying because the coefficient is not constant. There is t in this term. So all the split systems are time variant system. We can conclude this, all the split systems are time variant system. So that's all. I have explained so many system properties: dynamic system and static system, causal and non-causal system, and time variant and time invariant system. Thank you.